In today's lesson, we're going to be looking at piecewise functions. So what a piecewise function is, it's a function that is composed of various functions kind of put together. So in this case here, how a piecewise function is denoted, you have your function f at x is equal to, and you see this sort of brace here, and what it's saying is if my x value is less than or equal to 2, then my piecewise function, my function is going to be the function 1 over x. After 2, so when x is greater than 2, the function is now going to be the function f at x equals 2. So what's going on here is you have a function that is being composed of a reciprocal function and then a horizontal line. And then they're put together, in this case, at 2. So let's take a look at evaluating piecewise functions just to get a handle on how this works. So for our first example here, we have the function at 1. So my input value is x equals 1. Okay, well, where does 1 occur? Is 1 in this condition or is it in this condition? So if you take a look here, this first condition here that I'm putting a box around, this is x is greater than 2, to which obviously 1 is not in there. So therefore, is it in this condition? And 1 is less than or equal to 2, so therefore the function is f at x is going to take on 1 over x attribute. So this is going to be f at 1 is equal to 1 over 1, which is 1. Continuing on here, now we look at f at 2. Now f at 2 is not in this condition here, right? 2 is not greater than 2, but 2 is less than or equal to 2. So this interval here contains the value of 2, in which case we're going to do the reciprocal function again, and this will be 1 over 2. And lastly here, we've got the function at 3. And you'll notice that the function at 3 is going to now meet this condition. 3 is greater than 2, so the function is going to output a value of 2. So now my function f at x now takes on the f at x equals 2, so just a horizontal line. So now no matter what input we have, my function is going to be outputting a 2. In particular, if x is 3, it's going to still output a 2. To further illustrate this concept here, now look at we're going to evaluate the function at 2.01. So notice 2.01 is not in this interval. This is all values of x that are less than or equal to 2. 2.01 is greater. So it's going to be in this interval here, 2.01. So therefore, again, even with decimal places, this is going to output a 2. On the other hand, if we evaluate the function at 1.99 here, what do we have? 1.99 is less than or equal to 2. So it's going to take on the reciprocal function, and this will be 1 divided by 1.99. And evaluating this, we get approximately 0.5. So for the following function here, we have the same setup. We have a break in our piecewise function at 2. You can see here when x is less than 2, it's y equals x squared. And when x is greater than or equal to 2, it's a linear function 2x plus 3. So let's take a look what this looks like. So make a rough sketch where you think the 2 is located on your x-axis. Now we're going to have the quadratic function until we approach 2. So my quadratic is going to go down here, go up, and then we're going to have our quadratic. Now at 2, we're not including x squared. The function changes to 2x plus 3. So at 2, we're going to put an open circle for now. The open circle signifies the fact that we're approaching this value here. In this case here, we'd be approaching 2 squared. So we're approaching 4 on our y-axis in terms of the output for y, but we don't know whether these two graphs line up. So as a quick check here, notice the function at 2 would take on our linear function, so it'd be 2 times 2 plus 3, in which case we get 7. So we actually do have a break in the graph here. And you'll notice, continuing on here, when we evaluate this at 2, we get the 7, and we have a linear function. So therefore, the function is going to jump up to a height of 7. And now we know this is a linear function. We know the slope is positive, and it's going to be increasing. So a rough sketch would look something like this. Okay, just to summarize this graph here, again, as I follow along here, we're approaching 2 from the left-hand side, and we're the function y equals x squared. As soon as we take a step to the right, we have a break in the graph. Again, this would be a point of discontinuity at 2. And then we continue on with a linear function, y equals 2x plus 3. Let's look at another. So for the following function here, you'll see this piecewise function takes on 3 values. When x is less than or equal to 0, we have linear. Between 0 and 3, we have another linear. And then greater than 3, we actually have a quadratic. So let's go ahead and graph these. When x is less than or equal to 0, let's label our origin here. Now when x is less than or equal to 0, we have a linear equation. This linear equation has a y-intercept at 1 here. So the y-intercept is going to be here. Therefore, the function is going to look something like this. Now notice here I included a solid dot on the x value of 0 because we're actually including, there's inclusion there. You can see it's less than or equal to 0, so we're going to put a solid dot on that value. Now, notice here at when x is greater than 0, my function 2x plus 1 is still approaching 1. They actually line up. If you were to take a 0 and sub it into this function, it would give an output of 1. If I take a 0 and sub it into this function, we also have an output of 1. Therefore, these functions line up. So this function will continue on. And the only real difference between the first function and the second is the second one has a steeper slope, but it's still linear up until we hit 3. So I'm going to actually continue on with a steeper slope until we approach 3, so maybe right about here. And then I'm going to go ahead and put an open circle there at the 3. Because again, we're not including x equals 3 as part of the function 2x plus 1. They may line up, and as a quick check here, we can actually see if I sub a 3 into here, we will get an output of 7. If I sub a 3 into here, we will not get an output of 7. So there's a break in the graph here, a point of discontinuity. Let's take a closer look as to what the function looks like greater than or equal to 3. Observing this here, we actually have a quadratic that opens downwards and has a vertex of 0, 4. To see this easier, we'll rewrite it. So you can see this function here has a vertex of 0 and 4. So the vertex of my function, and also you can see the quadratic is going downwards, right? The leading coefficient is negative. So if I were to sketch this quadratic in its full form here, it's going to be a vertex at 0, 4, so somewhere here. Then the quadratic is tending downwards. Now the quadratic is going to be hitting the x-axis at plus or minus 2. So a rough sketch of this quadratic would look something like this. If I were to kind of sketch this quadratic on here, the full thing, it would look something like this, where this is 2 and this is negative 2. And then you'd have a rough sketch of your quadratic negative x squared plus 4. Right, obviously this is the vertex 0, 4 here. So we kind of have to, when does this function kick in? Well, this function kicks in for my piecewise function when x equals to 3. So if I sub a 3 into here, what is g at 3? Well, g at 3 is 4 minus 3 squared, which is 4 minus 9 is negative 5. So 3 negative 5, which is down here, is where our function kicks in. So what will happen here with this function is it'll continue on being a quadratic that opens downwards. Now notice here, this is not the vertex of my quadratic. My quadratic vertex is somewhere up here, right? And the quadratic kind of goes down like this. Your piecewise function is kicking in at the value 3, negative 5. All right, and now at this value, we should put a solid dot because we're including that. And now we have an example of another piecewise function, a little more complicated of one, but still 3 pieces to this piecewise function. A linear, a steeper linear, and then a quadratic, the tail end of a quadratic. Again, to remind you guys, this is not the vertex. The vertex of the original function was all the way up here. Okay, let's take a look at another example. So this piecewise function is saying that when x is not equal to 2, we're going to output the function x squared minus 4 divided by x plus 2. And when x is equal to 2, we're going to output the function g at x equals 3. So what we want to do here is take a closer look at what happens when x is not equal to 2 here. In particular, focusing on this function. So focusing on this function here, you can see that obviously you have difference of squares in the top. You can use that to factor, and we have cancellation here. But what allows us to cancel these off is the fact that in our assumption, x is not equal to minus 2. So therefore, this function, x squared minus 4 over x plus 2, will actually simplify to become x minus 2, just a linear function, provided x is not equal to minus 2. So therefore, we really have a linear function here in the top, and then just a horizontal g at x equals 3 in the bottom. But now keep in mind, this horizontal is just at a singular point, so it's going to look different. So taking a look at this function, what you really have here is the function is going to be x minus 2 everywhere, but x equals to negative 2. So really we can graph the entire function here. So let's say a rough sketch of our function might look something like this. This is the graph of y equals x minus 2. However, at a singular spot, that is at negative 2, the function has an open circle there. And then the function takes on a value of 3. So it jumps up all the way up to here, solid dot at a height of 3. So what we have here is we have a linear function, x minus 2, until we hit negative 2, jump in the graph all the way up top, and then it continues on all the way over here. So again, we have a point of discontinuity at -2. This function, again, is completely linear everywhere but at -2. And then we have that jump in the graph all the way up to a height of 3. All right, let's take a look at piecewise functions and how that's used to define absolute values. Typically, absolute values are defined as if your input is positive, it just outputs a positive value. If your input is negative, it just changes the negative to a positive. But we've never defined algebraically how do you change a negative to a positive. Well, how you do that is the following, using a piecewise function. If you look at the absolute value of x, what it's going to do, if x is greater than or equal to 0, you're just going to output x, right? Think about this. If absolute value of 5 is 5, right? 5 is greater than or equal to 0. Absolute value of 0.01 is 0.01. Absolute value of a half is a half, because all of the input values are greater than or equal to 0, and therefore they're just going to output x, x, x. However, if we take a look at the absolute value of 5, we know the answer is 5. Obviously, we know the answer is 5. How do you do that algebraically? How you do that algebraically is just multiply by a minus sign. Because what's happening here is you know your input is negative. I know it's less than 0. So by multiplying by a minus sign, we would have an algebraic way to describe the absolute value. So in this case here, the absolute value of -5 using our definition is going to be equal to -5, in which case we get 5. Right? The absolute value of -0.01 using our piecewise function will be -0.01, which is 0.01. And lastly, absolute value of -0.5 is -0.5, which again gives you +0.5. So now we have an algebraic way to define absolute value. Let's take a look at graphing this and see what it looks like. Again, if I go to graph this function here, notice that when x is greater than or equal to 0, it's just going to output a linear equation, y equals to x. So it'll look like this. And we have a solid dot at 0. Now when x is less than 0, what it's going to output is -x. So what'll happen here now is it's going to output y equals -x. So now everything's going to go downwards and go like this. So what we have here really with your absolute value is this portion of the graph is y equals to x, and this portion of the graph is y equals to -x. All right, let's take a look at graphing a piecewise function, which involves an absolute value. So notice for the following piecewise function, at x equals 6, this is where we have sort of the two functions are being put together. One is the absolute value of x minus 5, the other is y equals -3. So therefore, when x is less than or equal to 6, we are outputting the absolute value of x minus 5. So whereabouts would it be on the graph here? When x equal to 6, you can see here that the function at 6 is equal to the absolute value of 6 minus 5, which is 1. So you've sort of got a solid dot here. Now, we have to take a look at what does the absolute value of x minus 5 look like on its own. Recall that one of your parent functions is the absolute value of x, and we discussed earlier absolute value of x. This is just a transformation. So this is a shift 5 units to the right, right? Your base absolute value function looks like this. And now we're transforming this, a horizontal shift 5 units to the right. And now our function would look like this. So therefore, if we were to graph this on our piecewise function, the minimum value would be at 5, 0. And our function would go down until we hit 5, 0. Then trend upwards until we hit 6, 1. And we've got that solid dot at 6, 1. Then greater than 6, the function actually drops down and takes on a linear function, open circle, and then a flat line at -3. So this piecewise function here, you can see has a point of discontinuity at 6. And we have the absolute value of x minus 5 function until we hit 6, including 6, I should say. And then we have a jump in the graph, a break in the graph, point of discontinuity, and it puts it together with a horizontal line at -3. All right, that concludes today's lesson on piecewise functions. Thank you.